Bismillahirrahmanirrahim. Our next topic is signal flow graph. Signal flow graph is actually another method to model the system. You have already discussed some modeling methods. You have represented your system through differential equations. You have represented your system through block diagrams, and now this is another method. You will represent your system using signal flow graph. This is actually the method of modeling of a system, and you may find the relationship between control variable and input variable using the signal flow graph. Bismillahirrahmanirrahim. Our next topic is signal flow graph. This is actually a pictorial representation of the system, another way of modeling the system. You have already discussed some modeling methods, how we represent our systems. You have already represented your systems by block diagram. You have already represented your systems through differential equations. By these methods, we are actually driving the relationship between our control variable and input variable. So this is more convenient method as compared to the block diagram, and we will find the transfer function using some rules. While we apply some rules on the signal flow graph, we will find the transfer function, we will find the relationship between the control variable and the output on the input variable. Just to recall that another modeling method, we'll see the signal flow graph now in the next lecture. We have already defined differential equation method of modeling, and we have already defined the block diagram method. Now we'll see the signal flow graph. What will we cover in this topic? First we'll cover some basic definitions with examples. What are the basic definitions? What are the things involved while constructing the signal flow graph, like branches and forward path and backward path, and then we'll construct our signal flow graph. We'll see how we'll construct by using the equations of the systems. How can we construct the signal flow graph? Then we will use Mason's gain formula to find the transfer function of the system, and then we'll see some examples, and then we'll see how can we convert our block diagram to signal flow graph. Block diagram is actually sometimes cumbersome to solve and difficult, and sometimes but all the times we have to redraw it again and again to reduce it into the canonical form to find the transfer function. So it is easier if we first convert our block diagram to signal flow graph, and then we find the transfer function using the Mason's rule. So first we'll see the construction and definitions, and then we'll find the transfer function using Mason's rules, and then we'll convert our block diagram into signal flow graph to find the transfer function. A signal flow graph is a pictorial representation of the simultaneous equations describing a system. It graphically displays the transmission of signals through the system as does the block diagram, but it's easier to draw and therefore easier to manipulate than the block diagram. Okay, now we come to the basic definition of the signal flow graphs. The signal flow graph is a pictorial representation of the simultaneous equations describing a system. It graphically displays the transmission of signals through the system as does the block diagram, but it's easier to draw and therefore easier to manipulate than the block diagram. So this is the same thing I have discussed, that signal flow graph is actually the representation of the system. We make signal flow graph, or we construct the signal flow graph using simultaneous algebraic equations of the system. Signal flow graph actually gives the cause and effect relationship of the linear systems that are actually modeled by algebraic equation of the system. So it actually gives the cause and effect representation of the system. Each and every equation of the system actually is in the cause and effect form, and this cause and effect form is actually depicted by the signal flow graph. And this method is developed by Mason to determine the relationship between system variables based on the line segments. And the advantage of this, the availability of the straightforward method for the complicated system to find the transfer function, and another advantage is the availability of the signal flow graph gain formula, which actually provides the relationship between the system variables without any reduction procedure, without any complicated reduction procedure or manipulation of the flow graph. And now we'll see some basic elements of the signal flow graph. We'll see some definitions of signal flow graph by taking a very simple examples, so that we can understand the basic definitions and then we can construct the signal flow graph at our own. So this is the very basic example. This is the simplest equation, y2 equals to a1 to y1, where in this equation, if we see it carefully, we have two variables y2 and y1, and y2 is actually the output and y1 is input. This is actually output, so we represent this variable by we represent all these variables by nodes. So output variable is actually, we are representing here as y2, and input variable is here as y1. So in this equation we have two variables, y2 and y1, and obviously so we, two variables we have two nodes. These are two nodes, y1 and y2. This a12 is actually the branch gain, and the branch is always directed from input to output. Here y1 is input node, y2 is output node, so it means that branch is directed from input to output. You can see here the arrow, the direction of the arrow is from input to output node, that is from y1 to y2. This is called the branch gain. So these definitions are written here. Variables y1 and y2 are represented by nodes, as I have said that the variables are represented by nodes. So normally nodes are arranged from left to right, that is from input to output, following a succession of cause and effect relationship throughout the system. So y2 is the effect, y1 is the cause. So further we'll continue the signal flow graph in the same manner. For the next, y2 will be the input, and if we have some y3 variable next, then the second branch will be from y2 to y3. A branch actually shows the transmission from input to output, and it always associated with a branch gain. Like here, for this branch we have an associated branch gain a12, and each branch have an arrow. Like here we have an arrow from y1 to y2. So y2 is equals to a1 to y1 is actually this is simplest system equation, and it is represented by the branch, and this branch is actually directing from y1 to y2. y1 is the cause, y2 is the effect, and this is actually the transfer function. Like this transfer function we have in the block diagram, we have a transfer function inside the block. Here we just write the transfer function we have in the block diagram as the branch gain. So this is the same thing we use in the block diagram. Here we have written here in the form of the branch gains. Next, we'll see the construction of signal flow graph from the simple algebraic equation of the system. We are taking an example. These are set of four algebraic equations representing a system. The first equation, we are going to construct signal flow graph for the system represented by these equations. The equations are y2 equals to a1 to y1 plus a3 to y3, y3 equals to a2 to 3y2 plus a4 3y4, y4 equals to a2 4y2 plus a3 4y3 plus a4 4y4, and y5 is equals to a2 5y2 plus a4 5y4. As we have defined that these are output nodes or output variables, y2, y3, y4 and y5 are possible output nodes, whereas y1 is input node, because in the first equation you can see y2 equals to a1 to y1, so y2 is output, y1 is input. Again for this term, y2 is output, y3 is input. So y3 is actually representing an input variable here for output y2. Please keep in mind that every term in the equation has a branch associated with it. So in the first equation we have two terms, a1 to y1 and a3 to y3. It means that when we construct signal flow graph for the first equation, we will have two branches, one for a1 to y1, another one for a3 to y3. In the first branch, y1 is input node, y2 is output node with a branch gain of a12, and in the second term of the first equation, y3 is input node, y2 is output node, and the associated branch gain is a32. In this case, y1 is input, y2 is output, so branch will be directed from input to output, that is from y1 to y2. In this case, y3 is input, y2 is output, and associated gain is a32, and the direction of the branch will be from input to output, that is from y3 to y2, and so on. We'll construct all these equations one by one. So it means that if every branch every term in the equation has a branch, it means that we'll have 1 2 3 4 5 6 7 8 9 branches. So we'll have 9 branches in the signal flow graph when we complete our signal flow graph. Let's construct it. Okay, now the first equation is y2 equals to a1 to y1 plus a3 to y3. We have just discussed in some detail that for the first term, y1 is input, y2 is output. So every variable is represented by a node, as we have already discussed. So we have 5 variables. y1 is input node, y2, y3, y4 and y5. So we have marked 5 nodes first here, that because we know that we have 5 nodes or 5 variables, so we have marked nodes as y1, y2, y3, y4, y5. In the first step, we have marked the variables, and then we have drawn the branches. So first branch is actually y1 to y2, directed from input to output with an associated branch gain a12. Another one is y3 is input and y2 is output. So this branch is actually directing from y3 to y2, that is from input to output. So normally the forward path normally in the forward path we draw on the straight line, and like this we have a feedback loop. We draw it either above the straight line or below the straight line. So we have drawn here y3 to y2 with the branch gain a32. So these two terms are represented by these two branches of the signal flow graph. Now we continue the construction of the signal flow graph. In the second equation, y3 equals to a23 y2 plus a34 y4. We already have these two branches constructed. So now for the second equation, we have another two terms. So we'll have another two branches in the signal flow graph. The first term is y3 equals to a23 y2. So it means this time y2 is input variable and y3 is output variable. So the branch will be directing from node y2 to node y3. This branch you can see from node y2 to node y3 with an associated branch gain as a23. So we have written here associated branch gain a23. In the next term, y3 equals to a43 y4. So in this time y4 is input node and y3 is output node. So here y4 is input node and y3 is output node. So the branch is directed from input to output, that is from y4 to y3 with a branch gain of a43. So you have constructed 4 terms. So you have 4 branches here in the signal flow graph till now. In the next equation, y4 equals to a24 y2 plus a34 y3 plus a44 y4. Here we have 3 terms. The first is a24 y2, the second is a34 y3, the third one is a44 y4. So it means we will have to construct 3 more branches in the signal flow graph. We will construct step by step. In the first term, y2 is input, y4 is output. So it means that y2 is input node. So we start from y2 and ends at y4. So the branch is directed from input node to output node, that is from y2 to y4 with the branch gain of a24. Now you can see that this time we cannot construct it in a straight line because we already have constructed line segments over the straight line. So we have constructed below the straight line from y2 to y4 with the branch gain of a24. Similarly, the next term is a34 y3. This time y3 is input node and y4 is output node. So we have constructed this branch y3 to y4. The direction is from y3 to y4 with the branch gain is a34. So we have two terms. The another term is A44Y4. So this time Y4 is input and Y4 is output. So the input and output variables are same. So it means Y4 is input and Y4 is output too. So we have this branch with a branch gain of A44. So now we have constructed three more branches for the third equation. Okay, now towards the final equation. The final equation is y5 equals to a25 y2 plus a45 y4. So this means this time we have two input nodes, y2 and y4. In the first term we have y2 as input node and y5 as output node. So the branch will be from y2 to y5 with the branch gain of a25. Again, we cannot move over the straight line because we have already drawn some straight paths here. Therefore we have constructed a line below the straight line with directing from y2 to y5, connecting these two nodes with a branch gain a25. Another branch is a45 y4. y5 equals to a45 y4. In this case y4 is input node and y5 is output node. So branch will be directing from y4 to y5. This branch y4 to y5 with the associated branch gain is a45. So we have written a45. This is the complete signal flow graph depicting all the terms in the signal flow graph. We can count 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 branches here. We have already discussed in the first slide when we discussed the question, when we were discussing the question, that we will have 9 branches because of these 9 terms in these algebraic equations. So this is the overall signal flow graph of the system describing by these 4 equations. Okay, now after the construction of the signal flow graph, we will see some basic definitions involved with reference to the signal flow graph and general definitions. Then we will apply the Mason's rule. We'll see what is the Mason's rule, and then we will apply the Mason's rule to the signal flow graph we have constructed. Some basic definitions are forward path. Forward path is actually a path from input node to output node, and along which no node is traversed more than once. So it is the path from input to output and along which no node should be traversed more than once. Here in the signal flow graph we have constructed for the 4 equations. We have multiple forward paths. Like one we have from node y1 to y2, y2 to y3, y4 to y5. This is a straightforward path from input y1 to output y5 and along which no node is traversed more than once. And the forward path is y1 to y2 and then y2 to y4 and then y4 to y5. This is another example. Again, this is starting from input node y1 and ending at y5, the output node, and along which no node is traversed more than once. That is, all the nodes are traversing only once. And the forward path gain is actually the path gain of the forward path. It means that all the branches encountering while this forward path, the product of the branch gains associated with this forward path with the specific forward path is called the forward path gain. For example, if we consider the first forward path y1 to y2 to y3 to y4 and then y5, it means that the forward path gain is the product of these branch gains, that is a12 multiplied by a23 multiplied by a34 and then a45. So the product of these branch gains is called the forward path gain. Similarly, if we consider the second forward path y1 to y2, y2 to y4 and then y4 to y5, then associated forward path gain will be a12 multiplied by a24 multiplied by a45. That is all the branches encountered in this forward path. The product of these branch gains is called a forward path gain, that is a12 multiplied by a24 multiplied by a45. We define the input node and output node. Input node is a node in which have only outgoing branches. This is also called the source node. Like we have here Y1 is this node which has only outgoing branches. It has only outgoing branches, that is a single branch from Y1 to Y2. Y2 is not an input node because the branch from Y4 is coming towards, the branch from Y3 is coming towards Y2. So it has an incoming branch too, that's why we cannot say that it is an input node. The only input node in this case is Y1. Similarly, Y3 has an incoming branch from Y4. Y4 has an incoming branch from Y4 itself. That's why the only input node here or the source node here is Y1. Similarly, the output node we define as the node which has only incoming branches, or it is also called a sink node. So the Y5 is here is an output node which has only incoming branches. Like Y4 has outgoing branch from Y4 to Y3. Similarly, Y3 has outgoing branch from Y3 to Y2 and so on. So there is only one branch with one node which has only incoming branches, that is Y5. So Y5 is here an output node. This is also called a sink node, and the source input node is also called a source node. Next is feedback path or feedback loop. A feedback path or feedback loop is a path which originates and terminates on the same node and along which no node is traversed more than once. The condition is that it should be start and ends at the same node. So we can see here that from Y2 to Y3 and then again Y3 to Y2, it's a loop starting and originating at the same node and along which no node is traversed more than once. Similarly, from Y3 to Y4 and Y4 to Y3, this is another loop terminating and originating at the same node and along which no node is traversed more than once. So these are the two loop examples. And when we say what is the loop gain, the loop gain is again the same definition, the product of the branch gains associated with this loop. So for this loop Y2 to Y3, Y3 to Y2, the loop gain is A23 to A32. For this loop Y3 to Y4, Y4 to Y3, the associated loop gain is A34 multiplied by A43. So the loop gain is actually the product of the branch gains of that loop. We have defined loops. Now we define the non-touching loops. Two parts of the signal flow graph are non-touching if they do not share a common node. It means that two loops are said to be non-touching if they have no node in common. For example, here Y2 to Y3 and then Y3 to Y2, and this loop Y4 to Y4 do not have any common node. That's why these are called the non-touching loops. If we consider Y2 to Y3, Y3 to Y2, this loop, and Y3 to Y4 and then back to Y4 to Y3, another loop, these two loops are not non-touching because they are sharing a common node Y3. So Y2 to Y3, Y3 to Y2 and then Y4 to Y4 are a set of two non-touching loops. Similarly, we have to see while we are applying the Mason's rule, the set of three non-touching loops or the set of four non-touching loops and so on. Up till where we found some non-touching loops, we'll find further pairs of non-touching loops. And the non-touching loops gains is actually the product of the two loops gains which are non-touching. For example, in this case, this loop and this loop, these two loops are non-touching, so the gain associated with that is A23 multiplied by A32 multiplied by A44. This is called the non-touching loop gain. Now we will define the general gain formula, which is the Mason's gain formula to find the transfer function or the transmission of the signal from input to output. The general formula is summation pi del I upon del. We'll define this. Pi is forward path. P is forward path. I is ith forward path. Pi means the signal flow graph has ith number of forward paths. Del I means del corresponding to the ith forward path. If, for example, if in your signal flow graph you have two forward paths, then the formula will become P1 del 1 plus P2 del 2 upon del. Or if you have three forward paths in your signal flow graph, this formula will be P1 del 1 plus P2 del 2 plus P3 del 3 upon del. Okay, sometimes in different books, authors used capital M for the forward path. So you can see that in some books there will be the formula will be summation mi del I upon del. So it means the same if you use this pi del I or you use the mi del I upon del. P is the number of forward paths, so it means whenever you are going to find the transfer function, first you will count the number of forward paths in your signal flow graph. Second is the del, pi del I upon del. We'll calculate the del according to the formula. You can see here in the third line, del equals to, this is more easier form of the del, that's why I'm explaining this. Del equals to 1 minus summation j pj1 plus summation j pj2 plus minus summation j pj3 and so on. This is actually 1 minus sum of all loop gains. All loop gains means summation pj1. 1 here stands for single loops. J for number of loops. For example, if your signal flow graph has 4 single loops, then this will become 1 minus P11 plus minus will be outside the bracket. Summation Pj1 will be P11 plus P21 plus P31 plus P41, bracket close. If you have two pair of non-touching loops, Pj2 means pair of two non-touching loops or the combination of two non-touching loops. So J here for number of combinations of non-touching loops you have in your signal flow graph. You will count the number of two non-touching loops and you will write here in the Pj2, and then you will count the number of three non-touching loops or the combination of three non-touching loops, and then you will write here. Please keep in mind that this has alternate signs, plus minus plus minus. Del equals to 1 minus summation pj1 plus summation pj2 minus summation pj3 plus summation pj4 and so on. We'll see how we'll expand this formula while we'll find the transfer function of the transmission rate. Next is del I. Del I is the formula for del I is same as the formula of del, but we'll consider only those loops which are touching forward path pi eliminated. If we have three forward path, for example P1, P2, P3, then we have to calculate 3 dels, del 1, del 2, del 3. If we have two forward paths, then we have to calculate 2 del i's, that is del 1 and del 2. So we'll see how we'll calculate it in the next problems. So the formula is actually pi del I upon del. Our steps will be, first we'll calculate the number of forward paths, then we'll calculate number of single loops, then we'll calculate pair of two non-touching loops, then we'll see the combination of three non-touching loops and so on, all the combination of the different types of loops present in the signal flow graph. Then we'll set our formula according to the number of forward paths. Like for two forward paths we'll have P1 del 1 plus P2 del 2 upon del, and then we'll calculate all del i's, for example del 1, del 2, and then we'll put in the formula summation pi del I upon del to find the final value of the transmission function or the transfer function. Okay, now we'll see a simple problem. Starting with this, we have already constructed the signal flow graph using the algebraic equations of a system. So we have to find the transfer function y5 upon y1 using signal flow graph Mason's rule. So we have already developed or constructed signal flow graph using algebraic equations provided earlier. Now we'll find the transfer function y5 upon y1, and we'll apply the Mason's rule. Then now we see how we'll apply the Mason's rule. Okay, we'll see that we have defined in the Mason's rule that a transfer function is equals to summation pi del I upon del, in which pi's are the forward paths. So it means that in our first step we have to count the number of forward paths. Here we have defined that y5 is in the output node, y1 is the input node, and we have to find y5 upon y1. We have already defined our forward path as from input node to output node, and along which no node is traversed more than once. We have defined forward path as the path along which no node is traversed more than once. So from y1 to y2, here first we see how many forward paths we have here in this flow graph. The first forward path is we have defined as m1, which is y1 to y2, y2 to y3, and then y3 to y4, and then y4 to y5. So it is a straight line from y1 to y5, and we know that the gain is actually the forward path gain is equals to the product of the branch gains. So all these are 4 branches, all have associated branch gains. So for first forward path gain, we will multiply the branch gains of all these 4 branches. So for M1, that is first forward path, the forward path gain will be A12 multiplied by A23 multiplied by A34 multiplied by A45. The second forward path from y1 to y5, you can see that from y1 to y2 and then from y2 to y5 directly. So there are 2 branches involved. The second M2, the second forward path gain is A12 multiplied by A25. The third forward path we can see from y1 to y2, then y2 to y4, then y4 to y5. These are all three forward paths. The third forward path gain is a12 multiplied by a24 multiplied by a45. So we have 3 forward paths here. No other forward path exists. You can see that in the definition of the forward path, it was stated that no node should be traversed more than once. Otherwise, we can say that y1 to y2, y3 to y2 to y1 to y2, y2 to y3, and then back y3 to y2, and then y3, and then so on up to y5. But this is not possible because no node should be traversed more than once. So we have 3 forward paths here, M1, M2, M3, or sometimes we say P1, P2, P3. That is A12, A23, A34, A45. That is a straight line. Then A12, A25, and then the third one is A12, A24, and A45 multiplied by A45. Now, as soon as we have counted the number of forward paths, so we'll set up a formula. Because we have 3 forward paths in the signal flow graph, so our formula will become y5 upon y1 equals to p1 del 1, p plus p2 del 2 plus p3 del 3 upon del. Because we have 3 forward paths, sometimes we may write it as m1 del 1 plus m2 del 2 plus m3 del 3 upon del. So it means that we have already calculated m1, m2 and m3. Now we have to calculate del, and then we have to calculate del 1, del 2 and del 3. To calculate del, first we have to find number of loops, number of single loops, number of two non-touching loops, number of 3 non-touching loops, and so on. So first we have to find the number of loops to calculate del. That's why we are watching here. How many loops here in this? The first one is L11. Here the first one shows the number of loop. The second one is for single loop. So these are all single loops. That's why the second subscript here is always 1. L11, L21, L31 and L41. So first is A23, A32. You can see here this loop. This is actually the following the definition of the loop, that starting and ending at the same node and along which no node is traversed more than once. So the first loop is A23, A32. The second loop is A34, A43. The third loop is A24, A43 and A32. The fourth loop is A44, starting and ending at the same node and along which no node is traversed more than once. Please note here that we can make a loop from Y2 to Y4 and then again Y4 to Y4 and then Y4 to Y3 and then Y3 to Y2. But this would not be a loop because in this pattern Y4 is traversing twice. So we have to keep in mind that no node should be traversed more than once. So in this case here we have four loops, L11, L21, L31 and L41, and we have already defined that loop gain is the product of the branch gains. So we have multiplied the branch gains associated with each loop to find the loop gains. Now after calculating the number of single loops, we'll see the number of two non-touching loops, and then number of three non-touching loops, and then number of four non-touching loops if exist in the signal flow graph. To calculate the value of del, please keep in mind that we are going to calculate the value of del, for which we are going to calculate loops here. So we have already calculated single loops. Now we'll see the number of non-touching loops. We have four loops, if you have remembered. In the signal flow graph, the first one is Y2 to Y3 and then Y2. And then we have for single loop, we have Y3 to Y4. If we see the first two loops, Y2, Y3 to Y2 and then Y3 to Y4 to Y3, then it means Y3 is a common node between these two nodes. So this is actually not making a pair of non-touching loops. So here the only combination of pair of non-touching loops is Y2 to Y3 to Y2 and then Y4 to Y4, which is called a self loop. So this is only one combination of two non-touching loops, and the non-touching loop gains is equals loops gain is the product of all the branches associated with these loops. So the gain will be A23, A32 multiplied by A44. And please note that L12 equals to A23, A32, A44, where 2 subscript is for pair of two non-touching loops. If we have more than one pair of two non-touching loops, then we'll say L22, L32 and so on. But here we have only one pair of two non-touching loops, so we have written here L1, 1 for first pair, 2 for two non-touching loops. So L12 equals to A23, A32 and A44. No other pair of non-touching loops exist here, and obviously if there is no other combination, then there is no combination possible for combination of three non-touching loops or four non-touching loops. So we have only one pair of two non-touching loops here. Now we'll calculate the value of del. We have already calculated the things required to calculate del. So the first we'll write the formula del equals to 1 minus summation pj1 plus summation pj2 minus summation pj3, and we extend the formula in the form of loops. So del equals to 1 minus L11 plus L21 plus L31 plus L41. As we have four single loops here, then again the non-touching loops, pair of two non-touching loops is L12. So the formula is 1 minus summation Pj1, which is the single loops, plus summation Pj2, pair of two non-touching loops. Now we have written the values of these loop gains here, which we have calculated in the last step. So we have calculated del in this manner. So del equals to 1 minus A23, A32 plus A34, A43 plus A24, A32, A43 plus A44 plus A23, A32 plus A44. Again, keep in mind the alternative sign. 1 minus Pj1 plus summation Pj2. So we have calculated del now. Now after calculating the value of del, we'll calculate the value of del i's. Here we have to calculate 3 del i's, that is del 1, del 2, del 3, because we have 3 forward paths. For each del I, we have to see the corresponding forward path. So for first del 1, we'll calculate del 1 for forward path M1. First forward path, we have considered M1 equals to the first straight line Y1 to Y2, Y2 to Y3, Y3 to Y4 and then Y4 to Y5. The first straight line in this, if you have noticed that all the loops L11, L12, L13 and L14 are touching this forward path, and we have defined del I equals to del. It means that the formula will remain same. Del I equals to del evaluated with all loops touching Pi eliminated. As all the loops are touching forward path 1, therefore we have to eliminate all the loops. And when we have eliminate all the loops, then the formula of del will become del equals to 1, because we have eliminated all the loops, because all loops are actually touching forward path. So del 1 equals to 1. The formula of del I and del is same, but we have to del I equals to del evaluated with all loops touching Pi eliminated. That is, we have to eliminate all the loops which are touching the corresponding forward path. Now to calculate del 2, we'll see the forward path 2. The forward path 2 is A1 to A2 5. That is from Y1 to Y2 and then Y2 to Y5. You can see here that the first loop, that is from Y2 to Y3, then Y2 is actually touching this forward path because Y2 node is common. If you see another loop Y3 to Y4 and then again Y3, this loop doesn't have any common node if we watch carefully forward path 2, because forward path 2, in forward path 2 3 nodes are involved, Y1, Y2 and Y5, and in this loop the two nodes involved are Y3 and Y4. It means there is no common node, so we have to consider this loop. Similarly, Y4 to Y4, Y4 to Y4 is also non-touching to forward path 2. Therefore the formula will become del 2 equals to 1 minus A34 A44. These two loops are actually non-touching to forward path 2. Therefore we have consider here del 2 equals to 1 minus A34 A43 A4 minus A44. Similarly, when we consider for del 3, we will see forward path 3, which is A12 to then A24 A45, that is Y1 to Y2, Y2 to Y4 and then Y4 to Y5. All four loops are again touching this forward path. Therefore, the formula will only become 1. So in this case, del 1 equals to del 3 equals to 1 and del 2 equals to 1 minus A34 A43 minus A44. So we have calculated all del i's. Now we have calculated all the required values, that is P1, P2, P3, del and del 1, del 2, del 3. So we'll put these values in this formula to get Y5 upon Y1. So we have put the value of P1, del 1. Del 1 is 1. So we have put the value of P1 plus P2 and then del 2 and then plus P3 del 3. Del 3 is again 1 upon del. So this is the required answer or the solution of this Y5 upon Y1. So we have applied Mason's rule here. We have seen that the steps in detail. First we have to count the number of first we have count the number of forward paths, then we have to set the formula according to the number of forward path. Here we have 3 forward paths. So P1 del 1 plus P2 del 2 plus P3 del 3 upon del. Then we have calculated the single loops and the pair of two non-touching loops and so on. Then we have calculated the value of del and then we have calculated the values of del i's, and then we have put all these values in this formula to get the answer. So we have calculated the required value of Y5 upon Y1 here. So I hope you have understand how we'll apply the Mason's rule to find the transmission rate or the transfer function of the signal flow graph. Okay, now we look at the back, what topic we have to cover under signal flow graph. So we have already defined some basic examples. We have seen that how we'll construct the signal flow graph using the algebraic equations of the systems. We have applied all the definitions we have defined for the construction of the signal flow graph. Then we see the Mason's gain formula, and then we see the steps in details. How we'll apply the Mason's gain formula, what are the steps to calculate the output upon input, or here we calculated Y5 upon Y1. So it is a usual practice that I explain all the steps in very detail in the first question. Then I hope all of you have understand. Then we'll do some more examples. I hope you will understand the steps I don't need to explain in details again and again. We'll see some more examples. We have already seen an example. We have constructed and then we have applied on the same signal flow graph the Mason's rule. And now we'll see some more examples. These examples will include that we have calculated y5 upon y1 in the signal flow graph. We can also calculate some intermediate outputs, the ratio of some intermediate outputs to the inputs. For example, y2 upon y1 or y4 upon y1 instead of the overall y5 upon y1. The procedure is slightly different, but we can apply the Mason's rule in the same manner or almost in the same manner we have applied to find the y5 upon y1. So we'll see some more examples in which we'll calculate some intermediate outputs or the ratio of some intermediate outputs to inputs. Then we'll see what are the rules to convert the block diagram to signal flow graph, what are the advantages of conversion of signal flow graph, block diagram to signal flow graph. Also, we'll see some examples of the systems of electrical networks or the mechanical translational networks. How can we construct signal flow graph for electrical networks or for mechanical systems or some other systems, and then we'll apply Mason's rule on those signal flow graphs of the systems to find the transfer function for that system. We can verify this using differential equation. We can verify this transfer function using block diagram method, and we can also model the systems by the signal flow graph. So we'll find the transfer function of different physical systems using Mason's rule.